All right, everybody. Welcome to another session of OpenShift Commons Briefing. My name is Beverly Kodak, and this week we have Zvonko Kaiser from Red Hat joining us to discuss a template the performance-sensitive application platform team here at Red Hat has developed to ensure that OpenShift runs any kind of high-performance workloads efficiently. And in this session, Zvonko will focus on AI/ML workloads. So without further ado, I'll let Zvonko introduce himself, talk about the topic, maybe a demo, and if you have any questions, we'll have a live Q&A session at the end. But feel free to add your questions in the chat wherever you're watching this live stream from, and we'll relay them back here. So with that, Zvonko, take it away.
Thank you, Beverly. As Beverly already said, my name is Zvonko Kaiser. I'm working with the OpenShift PSAP team, which is responsible for enabling hardware accelerators in OpenShift. We've been working with GPUs the last several years and closely with NVIDIA to enable GPUs and make it a first-class citizen in OpenShift. This session will cover some of historical bits and pieces we encountered during the way on enabling GPUs, first on bare metal, then on OpenShift, and we will explain what we've done and what SRO is and how we used SRO to enable not only GPUs, but also other accelerator cards in OpenShift. So without further ado, we are going to start what we'll be discussing today. We will cover a lot of topics. This is just an excerpt from the complete presentation. We're talking about container engines, bootstrapping, clusters, autoscaling, metrics, accelerators, workloads, building blocks. To show you step by step how an accelerator is enabled first on bare metal and then on OpenShift. So let's start with the first topic, which is runtime hooks. So we have on the one side, if you want to run a container, you have an engine and a runtime. And especially for GPUs and other accelerators, we need a functionality which is called a hook. A hook is nothing else than a callback during the container lifetime. We have a pre-start hook, post-start hook, and post-stop hook. And NVIDIA is using mainly the pre-start hook to enable the GPU. Hooks can be used to enhance the functionality of a container runtime with the functionality that the container runtime does not have. And in this case, it's to enable a GPU in a container. And what the NVIDIA pre-start hook is doing is mostly it bind mounts devices, binaries, and libraries into the container from a host. This way, it makes sure that the host and the container are in sync regarding the versions running on the host and in the container. So the pre-start hook configures the container to use GPUs. So speaking of mounting files in a container, since we are running on a RHEL platform, we need to cover another really important topic, and this is SLinux. Everybody who mounted any volumes or mounted any files from a host into the container knows that something is happening with SLinux in regards. So I just want to illustrate what really happens when you're doing mounts from the host into a container, and that's a crucial important point for the NVIDIA pre-start hook because it's getting the files from the host into the container. SLinux is nothing else than a labeling system. So a host, we have here all the blue labels is the host context. All the red labels are the container context. And container and host are two distinct SLinux domains. The blue labels or the blue colors know how to talk to other blue colors and how to talk to processes and how to work with files. On the other side, all the red stuff is the container SLinux context. All the red stuff knows how to read red labels, how to read red files, and how to work with red processes. So what you're essentially doing if you're mounting files from the host into the container is that you're introducing blue labels into a red domain. The red labels do not know how to handle those blue labels, and that's why you're getting always a permission denied if you're not dealing with SLinux on a RHEL system. So And one thing what people are doing is running the container privileged, but they don't really know what's happening if they're running the container privileged. The crux here is a privileged container has, now that we're seeing all the container and host are blue, that the container now can do everything with the files and processes as well on the host. Containers running privileged are having a special SLinux type, which is the SPC_T, and SPC_T can interact with any labels from the container and the host. So this is a bad thing to do to run a container privileged. What then people are doing is relabeling host files. But this means you're now introducing red labels into the blue domain, which can break the host content. And this is one worry of NVIDIA. If we are changing the devices on the host, that it breaks things on the host. We have enabled the container, but now the host is broken. So the solution for this is write a SLinux policy to introduce new types, what NVIDIA has done for the devices, libraries, and other files that's mounted in the container, and write a SLinux policy to allow the container to read these special files or special entities from the host. This is illustrated by the purple labels. It can be read by the host, and it can be read by the container, and the container has to not run any more privileged. So this is the part on the bare metal, how to enable GPUs in a container on a bare metal host. I've posted here the SLinux policy we've written for NVIDIA to enable that GPU in the container. An updated blog post about how to enable NVIDIA GPUs in containers on bare metal on RHEL 8 with all the updated SLinux policy for RHEL 7 and RHEL 8. And for people who are curious how a simple Prestart Hook works, I've also included here a directory for a simple, I call it OCI decorator. It's a Prestart Hook, which is backed by a config file to introduce, which can be used to mount devices, files, and other libraries from the host into a container. So now that we know that how it works on a bare metal, we need to think how to enable it on OpenShift. And one really important topic is bootstrapping heterogeneity. So if we are taking a default install with 3 master nodes and 3 CPU nodes, we can use a machine set to scale a cluster with your GPU node. So you can just use a CPU machine set that you have already in your cluster installed, change the instance type, scale it up, and you have a GPU node. The problem we have here is we have now a heterogeneous cluster. From the OpenShift point of view, we have 3 workers. OpenShift does not know that we have a GPU node. It knows that we have some CPU. It has only the notion of a worker. So what we've done in this case is, let's first zoom into the GPU node to show some features that you might have on a node. So for example, a CPU may have AVX512 CPU flex instructions, has a specific kernel, and is running a specific operating system. On the other side, this node could have a GPU, an FPGA, or NIC. So every node could have features that are interesting to different parts. We can use those features, for example, for optimized workloads. If you're optimizing your workload for AVX512, you want to have your workload run on an AVX512 node. If you have GPU workloads, which is special in this case, you want to run your GPU stack only on GPU nodes. You don't want to create a DIMM set, and the DIMM set is occupying the CPU nodes and the GPU nodes. So what we've done is we introduced a software which is called Node Feature Discovery. We've written an operator for it, so it's available in OpenShift. And what does Node Feature Discovery does is exposes node features as labels. So we have labels for CPU flags, for the kernel, for operating system. And as you see on the right side, PCI 10DE. 10DE is the PCI vendor ID for NVIDIA. So we have now a label where we can steer either with a node selector or pod affinities and anti-affinities, pod to the right node. Optimized workloads can now be placed on the right node, as I said, GPU stack on the GPU node, AVX 512 optimized workloads on the AVX 500 nodes. Why is this important? Workloads that are optimized for AVX 512 will not run on any other. You will just get a legal instruction. So you want to make sure that your pod lands on the correct node. I've added here some links for node feature discovery and how we are using also NFD for multi-architecture image builds, optimized low-level libraries for OpenShift, and how to steer those libraries and workloads to NFD. We have upstream NFD and the operator and a downstream version, especially for OpenShift, to just test it and run through QE to make sure that every NFD release is working flawlessly on OpenShift. And we have NFD since 4.2 as a GA feature in OpenShift. So now that we have bootstrapped our cluster, we know where our GPU node is. We need to think about how to enable the software, the NVIDIA complete stack on OpenShift, and especially keeping in mind that the default operating system is Red Hat CoreOS. So we started thinking about how we can support immutable hosts since OpenShift 3.8. And we've done some experiments on Atomic. And what we've come up is a thing called a driver container. A driver container is not only a delivery system for kernel modules, but it's also a image that handles the drivers and starts daemons that are needed, creates some syscontrols, and all the things a privileged container would need to do to enable the hardware. So the first thing what we're going to do is deploy a driver container. The driver container contains the modules, user space, and the hook. After the driver container is deployed, we are running a small validation step, the driver container validation. It's a small workload that uses the accelerator just to verify that the drivers are loaded and we can access the hardware. In this case, we are running CUDA vector add. The nice thing about CUDA vector add is it allocates memory, so we know that memory is working, does some computation, so the compute cores are working, and we can be sure after we are running CUDA vector add that the drivers are installed correctly. Step is the device plugin. The device plugin is the piece that exposes the accelerator to the cluster as a extended resource. So pods can allocate an extended resource and can be scheduled. So that's what we are doing as a next step. The device plugin validation is simply the same workload before, but just allocating an extended resource. So we want to make sure that the extended resource allocation works, and again, that we can run a GPU workload on the cluster. We have enabled the hardware, we expose it to the cluster. The next step is monitoring. So we are setting up Prometheus and Grafana, adding metrics, a custom node exporter that exposes GPU metrics, and we are also adding alerts so that it's visible in the cluster if something happens, if it's overheating, malfunctioning, and stuff like that. When monitoring is done, as an optional step, we can deploy a sidecar container for NFD. NFD has a hook mechanism where you can exploit NFD to extend the labeling system with your custom sources. And in this way, we are using the sidecar container for NFD to expose more sophisticated features of a GPU, like the GPU type, the GPU name, the memory, the CUDA cores, firmware version, driver version, and stuff like that. So in the case of AI/ML, you want to use, for example, a V100 for training and want to use a T4 for inferencing. So with the feature discovery and those exposed new labels with a prefix like NVIDIA.com, you have more fine-grained scheduling to steer your workloads to a specific GPU nodes. And summing all of those steps together is the special resource operator we have developed. This pattern repeats for most of the accelerators we've been enabling on OpenShift. Some need more features, some need less features, but as SRO is so extensible that you can add as much states as you want, or just leave it just by the driver container. SRO is also, sorry, is also capable on handling several driver containers for several vendors, and it really depends on the accelerator stack, what it's really needed and what needs to be deployed. We will now see also how SRO can handle updates in a OpenShift cluster. SRO has a mechanism for templatizing manifests so that you can inject runtime information like the kernel version, operating system version, and other stuff directly into the manifests you're exposing. And all of this, I see it SRO as a small state machine, because if you are deploying the driver container, it makes no sense to deploy the device plugin in parallel because it will just not work. We have some parallelism. We are steering everything with labels. So in SRO, we have a sequential approach. And then where it's capable, we are also running stuff in parallel. So for example, when we are deploying the device plugin, we are running the monitoring, feature discovering, and other parts in parallel to enable it in SRO. And SRO has been used with several vendors now. Prime example is now NVIDIA. We have Solarflare also used SRO to enable their hardware. And I will get back to another use case where we used SRO as a feasibility study or as a POC vehicle to enable hardware on OpenShift. Besides that, SRO also supports some more configuration. We can add hard or soft partitioning. I will come back to that later. We can choose the driver versions. We can use and some other configurations for driver container building. And all of those states are driven by custom manifests that are in a config map. So during the runtime of SRO, you can live edit your config map, and SRO will reconcile all your custom manifests that you're working on. And if you wanted to, for example, test new features, you could edit the config map for the driver container, enable some settings, SRO will reconcile, and the complete stack would be updated. Let me get into detail how SRO is dealing with updates. So let's start with the normal use case. We have deployed NFD and SRO. So the first step is NFD detects the kernel version and labels the node. We have a worker node, kernel running 4.18.0.80. The NFD worker daemon set detects it, sends a message to the NFD master, and the NFD master through the Kubernetes API labels the node and says, okay, I'm running with kernel 4.18.0.80. The next step is SRO reads those configurations, uses build configs to build a driver container for 4.18.0.80 and pushes it to the local image registry. After it's pushed into the image registry, SRO will deploy the driver container, and the GPU driver daemon set will pick up this from the internal build and enable the driver container and the driver and the accelerator, and the other steps are followed. So what happens if an update comes in? NFD will of course detect it, sees that we have a new kernel version, will relabel the node, and SRO will detect this mismatch and will use this new information it gets, this runtime information, inject it into the build config and say, okay, build me now the driver container for this specific kernel version, push it again to the image registry. SRO will update the GPU driver daemon set, add the new version, and this new version will be pulled by the driver daemon set, restarted, and the complete stack will be also restarted so that all those new changes that are coming with the driver are applied to all the to the complete stack that is already deployed. Special resource operator is a way how to enable special resources the OpenShift way. I've included several links here. The first link is the GitHub repository. The next link is how to use entitled image builds to build driver containers with UBI on OpenShift, which we are using to build the driver containers to always stay in sync with the kernel versions and the user libraries and all the tested and bug fixed and CVE tested UBI images. I've written 2 blog posts, part 1 and part 2, for those curious on the inner workings of SRO. Part 2 is really how API is working, how OpenShift Kubernetes works internally, and what SRO building blocks we are providing to enable hardware. The last link is how to deploy the NVIDIA GPU operator on OpenShift and using the cluster autoscaler to scale the Rapids image. For those curious what the relation between the NVIDIA GPU operator and SRO is, the NVIDIA GPU operator is a fork, a one-to-one copy of SRO. After NVIDIA has picked up SRO, they of course relabeled it, done some extension to it to their needs, but mostly it works like I just described. So what else can we do with GPUs? We have the initial GPU cluster configuration with 1 GPU node. What works today is we can use the cluster autoscaler for on-demand GPU nodes. So if you have for example, if you have a pod pending with the extended resource NVIDIA.com, you can create a cluster autoscaler with a specific machine sets to autoscale GPU nodes. We are currently working also on enabling HPA to work with GPUs. Before I mentioned hard and soft partitioning. What we mean in hard soft partitioning is hard partitioning is taints and tolerations. So SRO is able to automatically auto-taint the GPU nodes with the extended resource. What we want to prevent with taints is that we only schedule GPU-only pods on the GPU nodes without having any CPU nodes interacting with our GPU nodes. The other way is to do soft partitioning, so to allow CPU and GPU nodes on the GPU nodes, but have priorities. So any GPU workload or pod that comes in with a high priority or low priority will have is first to run on the GPU rather than CPU node. We can also, of course, combine those hard and soft partitioning, combining both, that we are only running GPU nodes, but now we have also high priority and low priority running on those GPU nodes. Another thing that's working with GPUs is quotas. So you can have quotas per namespace, multiple namespaces for CPU mem, and of course for extended resources like the GPU. So with all these features, you can go on and maybe create even some more roles. You can have clustering nodes with specific roles for GPU training or for GPU inferencing, depending on your GPU type or what you exactly want to do in your GPU cluster. Per default, the infra-only pods and master nodes are already tainted, so you could also have taints on your CPU nodes and priorities if you have a mixed cluster where you're running CPU workloads and GPU workloads, and all those pods can be repelled or attracted or not scheduled with affinities, anti-affinities, or node selectors. The other thing I want to mention, if you have several GPU nodes, you want to have them interconnected with a high-speed interconnect. So this is where Maltese comes into place. And for those people who don't know what Maltese is, Maltese provides secondary interfaces to the pods, so you can have a separate data plane for a GPU node so that you won't worry that you are interacting with the API. So with the GPU nodes and NVStack, you already have something like a separate compute plane, independent and out of reach of the API. You're just running your workload on the GPUs. And now, not to use the internal network, but a dedicated network, you can use Maltese. And what we are currently working on is we've used SRO to show and make a POC how to enable RDMA completely containerized in OpenShift with running either over InfiniBand or Ethernet. So all the pieces like the Moffett stack, the GPU direct driver, and all other pieces that we need for GPU interconnects are containerized and running on Red Hat CoreOS. The company or the vendor we are currently working on used again SRO as the driving vehicle to test this POC, and now they're implementing on top of SRO and with this template their own operator to enable RDMA over InfiniBand or Ethernet for GPUs. I've included here some demos I've done in the past. First link is the Flowers demo on OpenShift, and we have also some CLI footage and running Rapids with GPUs on OpenShift. I've also included a link to a Google Doc, how to enable GPUs with OKD 4.5. And the future work we are doing is, one is firstly GPU Direct to enable fast interconnects. And the other future work is Mixer-Port. Mixer-Port is a new feature of the new GPUs to slice up the GPU in several distinct pieces. So a big GPU can be sliced up to 7 pieces, and those seven slices are recognized by OpenShift as 7 dedicated GPUs. So this is some of the new features that's coming up, and we are working closely with NVIDIA to enable this in OpenShift as soon as possible. And this is also my last slide. Do we have any questions?
Indeed, we do. And Zvonko, that was a really great presentation. So someone is asking, SRO is available on OKD. Is it also available on top of FCOS? I'm assuming that's Flight Control Operating System, but I could be wrong.
That's Fedora CoreOS. I just switched to my terminal OCG cluster version. We have here a OKD 4.5 running. We don't use SRO here. We can use the NVIDIA GPU operator here. I've included the instruction how to use it. OCG pod. We have all the usual suspects on OKD running. And if I do a OCG nodes, this is my last OC describe node grep 10DE. I just want to show that NFD works out of the box. We are currently working on adding it to the community operators on Operator Hub so that it shows up in Operator for OKD as well. So we have a GPU in here, and if we grep for the extended resource, we can see that we have 1 GPU in this cluster. Zeros are allocated, but we have 1 available, and we are running here on OKD. OC debug node nodes. Debug node. Just to make sure that I'm not faking anything. To release, we are running on a Fedora CoreOS 32, working with NVIDIA to add Fedora support into their driver. Currently, we have to build our own driver container and push it to a registry, but working with NVIDIA to add this in the official repositories.
Great,
Question.
great. So we also have a question from James. He's asking, is that AMD MX GPU?
We don't have, there's no AMD here.
Okay.
What is the question? Is the question if we are engaging with AMD to support it in OpenShift, or is the question if we are using right now an AMD GPU?
I guess we could answer both. So are we engaging with AMD right now? And if no, or is there a plan to? Right
now? I'm not using any AMD GPU,
Okay.
but AMD has all the pieces I described here already posted. They have a Prestart Hook, they have the device plugin, they do not have any metrics, they don't have any monitoring. So technically it should work. There were some discussions on enabling AMD, yeah.
Okay, so AMD does work. You can confirm that, right?
I haven't tested it myself.
Mm-hmm.
I'm just saying all the pieces are there, the Prestart Hook, the device plugin, the drivers. I don't know if it works on Red Hat CoreOS.
Okay.
They haven't built a driver container. So from the technical point of view, with some hacks, it should work.
Okay, thank you. So, we have a question here. Someone's asking, so if I understand correctly, we do not change the Red Hat CoreOS or Fedora CoreOS. The operator will install a driver container and push it to OpenShift stroke OKD default registry, and that enables the GPUs on OKD. Is that correct? And I could repeat that question.
Yeah, I understand the question. So
okay.
What we wanted from the beginning, even when started with Atomic on OpenShift 3.8, we didn't want to touch the host at all. So we are not doing anything on the host operating system. Why? We want to make updates as smooth as possible. So we don't want to write somewhere to some suspicious directories like /opt and then clean up afterwards. If we are rebooting the node, we don't want to have any traces of anything on the node. So everything is in the container. SRO pushes us to the internal registry. NVIDIA has used a different path. They are building their drivers on demand in the driver container. So if you are deploying the NVIDIA GPU operator, it will build the driver on demand right away as a pod on the cluster. Why SRO has done it with the internal registry? Because we wanted also to support customers that are in disconnected environments. So what SRO is doing, it first deploys the driver container, and if it sees that we are in error image pool or image pool backoff, it will deploy the build config. This way, a customer could push a custom-built driver container to their internal registry upfront, and SRO will just pick up this driver container without being connected to the internet. Because right now, we have to fetch the driver from the internet to build it.
All right. Thanks for that, Zvonko. We also have another question from YouTube. Daniel's asking, are kernel headers included in Red Hat CoreOS?
They are not included. What you have to do is to entitle your cluster. I've posted one of the links on NFD, cloud on the NFD Node Feature Discovery page is the link how to entitle your cluster, how to build Red Hat software. So you need a subscription to get kernel devel, kernel headers, and kernel core that's needed for the kernel driver. In the Red Hat CoreOS case, you need an entitled cluster to get access to this to the software. On Fedora CoreOS, we don't need it. There's no entitlement. We can use it right away.
Great. Thank you. So we also have another question. So can you elaborate on how to achieve the GPU only high priority, low priority jobs? And is that something, or is that how we can be more granular on non-GPU workload scheduling?
Okay, let me just think what would be the ask of this question. One aspect is the granularity, fine-grained scheduling on the type of GPU and the features of GPU. This would be like I'm targeting the workload for V100s or T4s. And the other aspect is the priorities. So every pod you can provide a priority that you custom define. And if you're using taints, only GPU workloads would run on a specific GPU node with these taints. So we are excluding like the CPU workloads if you're using taints. This would be like the hard partitioning part, where we are repelling all CPU workloads. And then inside a GPU node or namespace, or how do you cluster your GPU nodes, you would have priorities. And you can add as much as you want to have priorities. I just included like high and low, but you can have a more fine granular priority classes from 1 to 10, 1 to 5, depends on really what you want to achieve. And higher priority pods have a higher priority, of course, for running, and will evade low priority pods. So you can be sure that your high priorities are running with a high at first on a GPU node.
Thank you. So here's another one from Sandrino. So he says, a month ago, he tried the NVIDIA operator on a test cluster, and the NVIDIA operator was trying to fetch kernel headers in the extended update support. And our entitlement does not, or their entitlement does not cover ESU. So does the SRO that you showcased today solve the ESU issue?
We know this issue. We are working on it. I cannot go too much into details, but on the NVIDIA driver container is instructions how to enable extended update support in the container for building it. But we are working on it to have this issue resolved in OpenShift, so that customers can easily fetch kernel devel, kernel headers, and kernel core for building their driver containers. Another enhancement we are working on is to provide a simpler way how to build driver containers. So this is currently in the working, to hide all those nasty details from customers, like where to fetch the kernel headers to enable as extended update support repositories, fetch it from somewhere else. So we are building something like a base thing for customers so that they can easily build driver containers without thinking of which kernel version I'm running, where do I get my dependencies, what do I need to enable, and stuff like that.
Thank you, Zvonko. I was just checking if we have any other questions, but W. Shari says thank you for clarifying her question. And oh, we have another question here. So the feature discovery sidecar will enable vGPU. That is scheduling cores, not a whole GPU, is it?
The sidecar container, the feature discovery.
So I guess this is a two-part question, yeah.
Yeah, it's a two-part question. Can you repeat the question?
Yeah, absolutely. So will the feature discovery sidecar enable vGPUs?
No.
Okay, no. So
it has nothing to do with vGPUs.
Okay.
So if you're running, for example, just annotation, if you're running, for example, OpenStack and install the vGPU compute server from NVIDIA, it will work to pass through with GPUs in VMs. And then if you're installing OpenShift on OpenStack, you just need to install the NVIDIA GPU driver, the NVIDIA GPU operator, and it will work. The vGPU is on a different level. It's not on the OpenShift level, it's on the infrastructure level.
Okay, all right. Thank you. So we also have another question here. So is the scheduler aware of the GPU load per node?
The scheduler is aware of the GPU in the sense that a pod is requesting a extended resource. And what the scheduler will do is to check if all requests or allocations a pod is doing can be satisfied by a node, and that's all. You have to remember that currently a GPU is allocated as a whole unit. There is no GPU sharing. So if you are saying a pod is allocating NVIDIA.com colon 1, it will allocate a complete GPU. And if you have only one GPU on the node, one pod with one GPU allocation will run on this node. There's no sense in the case, for example, a pod is using half of the memory, I could schedule another pod. No, the GPU is seen as a whole unit, and you can only allocate a complete unit in the cluster.
So is there any something like a GPU pressure indicator in that case?
You could do that. For example, SRO has sample implementations of the metrics and alerts. We are, for example, alerting the customer if the GPU is idle and he's wasting money, or if the temperature is too high, you have a problem with cooling. That's the same thing you could do for pressure. You could take out the specific metric which tells you how much memory is used or how many cores are used, and expose this as a alert. If a given threshold is overridden, you can alert the cluster or the administrator or the user who is sitting in front of the console that like 99% of the GPU is used. This will aber not be fed back into scheduling decisions. As I said, the GPU is as a whole unit, and what you do on the node with the GPU is one pod, and this will not make any decisions on the scheduling. If you can allocate the GPU, you can do whatever you want with the GPU.
Okay. So is it possible for the pods to share?
Technically, yes.
Okay.
But not in OpenShift right now.
Okay. I guess we'll jump back to vGPUs again. So in vSphere, if one enabled vGPU licensing, then OpenShift via the NVIDIA GPU operator. I'm sorry, I'm trying to understand this question as well. So if one enabled vGPU licensing, then OpenShift via the NVIDIA GPU operator will be able to see this. Does that question?
Everything that is visible by the operating system and exposed as a PCI device, which is done in vSphere or in OpenStack, which is essentially like something like a pass-through, PCI pass-through, and the operating system that is deployed on top of this infrastructure. And if the GPU is detected like a normal device, which I suppose it is, the NVIDIA GPU operator will work.
Okay, that's clear. Second, let me see if we have any more questions coming in. Okay, I think we're clear. Zvonko, thank you so much for taking the questions.
My pleasure.
Yeah, that was a very useful session, and especially right now with GPUs being such a hot topic. I'm just gonna give it a few more seconds to see if we're gonna get any more questions. Okay, we're in the clear. So thank you so much. This was a very great and timely session. Always insightful, always educational. Huge shout out to Chris Short as well for promoting this session, and making the live stream very seamless. And I guess with that, we'll let you all get back to your days. Thank you so much for joining.
Thank you.
All right.